Yes, more or less.
Pleasure next to introduce Giovanni Solda, who will speak to us about multifunctions, computing sequentially continuous multifunctions.
Right. Thank you very much. Thank you for the introduction, and thank you for inviting me. Right. The title is not quite precise, but yes, it's fair to say that I will be telling you something about multifunctions, in a certain sense computing something which is in a certain sense sequentially continuous or sequentially discontinuous. And this is joint work with Arno Pauli, as he pointed out this morning. So I should also say something along this line was also explained by Arno during the CCA. So I do apologize for all the people that are here and that are not there, because instead of hearing the beautiful talk by Arno, you just, well, hear me rambling about something similar. But anyway, so let's start with some background. So a represented space, I mean, as I assume most of you know, is a represented space is simply a pair x and delta x, such that x is a set, and we want it to be represented by this function delta. So delta is a partial surjection from their space to this space. And for every point, we say that so yeah, for every point in our set X, we say that a certain P, so that its image is this X, is a name of the X we started with. And a relation between X and Y essentially is called a partial multifunction or a problem. I will use these two terms interchangeably. Yeah, it's simply, yeah. So a problem is simply a relation between X and Y. So the domain of f and f of x are defined the obvious way, and even if it wasn't particularly obvious to you, it was defined by Linda yesterday. So, so technically speaking, I mean, there is a reason why I introduced new terms. So technically speaking, the category of relations and the category of partial multifunctions are different. So it makes sense to actually use different terms, although this will not be the main focus of today, of course. So, but something that will be particularly important for today is the following thing. So given a problem between x and y, we say that a function between a partial function between x between bar space and bar space is a realizer of f. So yeah, whenever big F realizes small f. So intuitively speaking, this diagram commutes. So for every point here, you want to be able to go around the diagram the two ways, and you want to essentially get the same result. So more formally, so we want that for every Q in the domain of sort of representation composed with your problem, it holds that if you first apply the realizer and then you go down the diagram the other way, you get something that belongs to f of the name of the point that you had. Right, this is a lot of words, but like the intuition of what is going on is not particularly difficult. And something that we will exploit is that this perspective allows us to define operations on problems. Okay, well, this is essentially a joke. I mean, I assume that everyone knows what a Turing functional is, but I want to sort of draw some analysis between this definition and the definition of a continuous function later on, so which is the main reason why I wrote this down. Anyway, so we say that a problem f Weihrauch reduces to a problem G, and we write it this way. If, as it was already said during the conference, if there are Turing functionals H and K, such that, I mean, this diagram works. So whenever you're given a realizer, whenever you're given a realizer G for the problem G, then you're able to produce via these functionals a realizer for F. But I mean, this was everything was already explained in previous talks. Yeah, something that I should probably say is that, so yeah, you can say that Fi is Weihrauch equivalent to G. So yeah, if the two relations hold, if Fi reduces to G and vice versa, and since this is an equivalent relation, it makes sense to study the lattice of the Weihrauch degrees of problems. Okay, but we will actually be talking about something more general in a certain sense. So we said that F continuously Weihrauch reduces to G, and we denote it with by adding an asterisk, a star on top of the reduction sign. So yeah, if there are continuous function H and K doing essentially the same thing that we wanted computable functions to do before, and something that we should essentially remember that continuous functions between, I mean, from bare space to bare space are functions that are approximable, essentially. So you can come up with h tilde from sort of finite string to finite strings that approximate the continuous function you're given. And so in particular, I mean, this is not surprising, it's about this is well known. So H can be seen as being computable with an oracle. In particular, this means what? That like we can repeat the same diagram as before, essentially by putting some letters where it's convenient to put them. So continuous Weihrauch reduction is just the usual Weihrauch reduction where but you also want to have some oracles. I mean, so yeah, your functions have access to some oracles that you have to decide beforehand. Okay, and again, we can, I mean, similar as we were doing before, we can define a lattice W star of continuous Weihrauch degrees of problems. Okay, and here we said that the problem F is continuous if it has a continuous realizer, and we say that it is discontinuous otherwise, so no continuous realizer for this proof guy. Okay. So something to notice is that the nowhere defined problem, so the problem with the empty domain, continuously reduces to every problem for essentially for trivial reasons. It's impossible not to produce a realizer for this guy. So yeah, because I mean, if you remember what the definition of a realizer was, you know, for every point in the domain, etc., this guy has no point in the domain. So I mean, this will essentially be a bottom element in the lattice of problems that you study. Something which is sort of peculiar about the continuous Weihrauch degrees is that sort of the identity is a second step. So you can see that every continuous problem reduces to the identity, and also vice versa. This is not something that happens for the computable degrees essentially, because because the computable degrees you can do strange things with the domain essentially. So at this point there's a question which is very natural to ask. So we have if we just restrict to the continuous degrees, so we know that there is a bottom degree, we know there is another degree, which sort of represents easy problems. Is there a minimal discontinuous degree? So how far can we go with this nice structure of degrees of problems? And the answer was actually given by, well, okay, I shouldn't spoil it, but like if we're picky enough with our choice of problems, I mean, there are some hints that seems to suggest that there is such a problem. So it was something that was already shown by Weihrauch. I actually don't know when. I mean, so it's in his book, but I don't know when it was originally proved, that if you just consider functions from bare space to bare space, then such a degree exists. So, you know, if we consider the degree of LPO, so the limited principle of omniscience, then this degree does the job. So what is LPO? This is simply the problem that accepts as inputs every point in counter space, and it outputs 1 if these points happens to contain a 1. So if it is not the constant 0 function, and otherwise it gives you 0. So it only gives you 0 if you started with a 0 point. So I'm introducing this because I sort of want to use this guy as an example in a later slide. Okay, so in the case in which we sort of restrict our attention to functions instead of multifunctions, we sort of have a satisfactory answer. But what happens if we actually check multifunctions? Well, the answer was given by Brattka. So in this case, it's particularly interesting to study this function here, which is what Brattka did in his paper, the discontinuity problem. So in this case, we should consider this problem here. So the input is any real, any point of bare space, and the output is, okay, so you fixed the universal Turing function in advance, and the output is essentially you exclude everything except at most one point. What is this point that you don't like? Is the result of applying this universal Turing functional to the point you started with. And what Brattka showed is that, at least for me, it's quite interesting. I don't know how to do this for the others, but assuming the axiom of determinacy, then this problem here does the job that, is what you were looking for. So for any f, for any partial multifunction from f to y, f is discontinuous if and only if it computes this guy. Which is no small thing, but that's all right. Well, I don't know if Vasco is here, but before I get sort of spoiled life on on YouTube, I should say that I'm actually cheating. So in order to use axiom of determinacy, you have to, you cannot use the axiom of choice. So you have to somewhat change the definition of what a problem is, because it's not, it's not immediate to find a realizer, to say that every problem has a realizer, but everything can be fixed quite easily. Okay, so in any case, if you if you use the full axiom of choice, then one can actually find a problem which is a counterexample to this phenomenon here. So you find something which is discontinuous, but does not continuously reduce to this strange guy here, to this discontinuity problem. And so what's going on here? So the point, in a certain sense, as we will say something more about it later, is that so what I did as for is a problem that if f is discontinuous, then it is actually continuously discontinuous. And what do I mean by that? What I mean is that so the following phenomenon happens. So essentially, you can read this sort of this equation here, so to speak, in this sense. So you want to say that so you try to produce a continuous realizer for your function f, and you say that the index of this function should be p. Well, thanks to the axiom of determinacy, you're actually able to come up with a continuous h that produces a point on which this candidate for a realizer fails. And this is what's going on here. And I should also say, so what Brattka, so in order to show that this guy here is discontinuous, essentially you use a generalization of the recursion theorem, to show that you can make something similar happen when this f is just this very, very general guy, in a certain sense. So yeah, I guess while you eagerly wait for the paper by Arno and me to be written, you should actually read the paper by Vasto. Okay, and we will say something about it later on. But so something to notice is, in a certain sense, how weird this principle, like this problem is. So, for instance, like the domain of this is the entirety of bare space, but like if you take any, if you restrict the domain of this guy to any countable set, then what happens is that this restriction not only happens to have, not only will it have a continuous realizer, to have a constant one, because, well, since you're only excluding, in this case, all of the points that you have in your domain will exclude just countably many points. So in particular, you will definitely be able to pick one of the uncountably many points that remain and sort of use that to construct a constant realizer for the problem that you're left. So in a certain sense, this is, this is a very weird problem indeed. So it makes sense to sort of restrict the attention to something tamer, maybe something that you, some form of discontinuity which is easier to have in mind in a certain sense. Okay. So and this is what we are about to do. So we want to restrict to study functions from x to y that are sequentially discontinuous. So what do we mean by that? So we require that there is a converging sequence in the domain such that it converges to something in the domain. If we restrict the attention, if we restrict f to this sort of converging sequence, then this function, this problem is discontinuous. And a function that will be very important in this in the study of these problems is the following. So ACCN, which stands for all or co-unique choice on n. And this is the problem that works as follows. So you're given an input an so an enumeration of a set, an enumeration of a subset of the natural numbers, which contains at most one point. So essentially, you should read your input as essentially, so as long as it says 0, you should picture it as sort of having nothing enumerated in your set. But as long as you're given something which is different from 0, then that guy is enumerated in the set. And what you want to do is to avoid the guy that's being enumerated by the input sequence. So which explains essentially the name all or co-unique choice on n. Okay, and as we will see, this is essentially the guy that every discontinuous function will compute. It's quite interesting that this guy is not immediately, it's not the most trivial intuition to have to say that the ACCN is discontinuous, but ACCN has a sequential interpretation in this sense. So by n, I mean the following set. So the number n will be represented by n zeros, then I put a 1, and then, well, I could put whatever I want. For simplicity, I say that I just attach a string of zeros after it. And by, okay, so closure of omega, I mean like the topological closure of the guide that I just defined. So I also accept the constant 0 as a point. So, and we can sort of define sequential ACCN as the program that takes as input any point in the closure of omega, and as outputs, it gives me the following thing. So if the input was this limit point, then we actually don't care. I mean, any point in n will be a valid input, a valid output. Otherwise, the point that I want to avoid is essentially the first component of the point that I was given as input. And it is not particularly difficult to see that we actually have a Weihrauch equivalence. So no oracle is needed here. So ACCN and sequential ACCN are actually are Weihrauch equivalent. And why? Well, just to see an easy example of a Weihrauch reduction. So to go from ACCN to sequential ACCN, okay, so you start with your input here, with your input enumeration of something, and you do the following thing. So as long as you don't enumerate anything, you're perfectly happy with sort of producing basically the limit point in the closure of omega. But as soon as something is enumerated in your sequence, then you say, okay, then so if let's say at step m you enumerated the point n, then simply what you do is you say, okay, then what I want to output is the point code of nm, and of course you will be done. I mean, whatever sequential ACCN gives you as an output, you can read that as a valid answer to ACCN, and the other direction, well, it's similar but backwards in a certain sense. So nothing surprising going on here. But the point is that, so now this guy is quite obviously discontinuous in a sense, because, well, like how can it possibly be continuous? I mean, if you decide that the sort of that f of the limit point is a certain infinite number, then it's essentially trivial to find a sequence that converges to, I mean, a sequence of natural numbers that converges to your limit point, but the image will not be able to converge because you forced f on those points to be different than the value that f of limit point is taking. Yeah, so not particularly surprising. But more is true. So as I was saying, it is actually the case that the following are equivalent for functions between x and y. So it is equivalent to be able to, to continuously compute ACCN and to have this sequence in your domain. So there is this the sequence AN, which converges inside the domain, and if you restrict your function to that to the closure of that sequence, you get something discontinuous. Okay, and let's see at least a sketch of the proof of what is going on here. So the first step is actually sort of admitting that I'm cheating to an extent, in the sense that I want to reduce. I want to just consider actually multifunctions from bare space to bare space. How do I do it? Well, I pre-compose and post-compose with respectively my with the representation of x and the entire representation of y. So if I had a converging sequence in x, I can essentially pull it up and find a converging sequence in the bare space, and then I will study essentially the induced function on bare space, which gives me values on the bare space. Now, okay, so what does discontinuity mean? Okay, maybe it wasn't the smartest idea I've ever had to put this on a slide, but so what does discontinuity tell you? Discontinuity tells you that for every y in the image of the limit point, so b is the limit point of the sequence that I found, you have to be able to find a neighborhood of it, and essentially a sequence of points in the rest of the sequence, such that the entirety of the f image of these points misses these open sets completely. And why is that the case? Because if it wasn't the case, like if you had even one point, one real in f of b, such that essentially you can hit it. So for every subsequent subsequence of your original sequence, you can hit it with something. Then you could use this fact to build a continuous realizer, right? And this is exactly what you don't want. Okay, so in particular, so of course there are, I mean, countably many of these guys because well, they're strings, so there are just countably many of them. And in particular, we can come up with an enumeration of them. So, and what we do is the following thing. So we scan E, so we scan the input that we are given, right? So because we're putting this implication, so we can assume that we're given an enumeration of a set. And we say that, okay, so as long as we don't enumerate anything, we're perfectly happy with producing a name of the limit sequence. But as soon as we're given something, what we want to output is a BJ. So if we know that the point we have to avoid, the natural number we have to avoid is n, what we want to do is we want to output a point whose image sort of misses the nth neighborhood of one of the points in the image of f. Okay, and then what we want to do, and then it's like to prove the reduction, it is enough to check. I mean, at the same time, the initial data that you were given, so the enumeration of the point, and the image, I mean, and the answer given to you by the function f, which is what you had to begin with. So what is going on here, essentially, so you either by checking these two things in parallel, you either find something that E had to avoid, and then you're perfectly happy because you just avoided, or you find that your point essentially so you find that your point misses some of the some neighborhood of the limit point, and then you're also happy because this is exactly what you wanted to know in a certain sense. Okay, so maybe this is not the, I mean, this is in a certain sense a bit chaotic, but in a certain sense, they try to figure out what happens for the case that Weihrauch was examining in a certain sense. So what happens? What does this all mean if we just have a function? If we just have a function, this whole process tells you essentially, I mean, in a certain sense, it tells you whether you will hit the limit point because you, I mean, because in the end, just by checking the image of the, by checking the point that is given to you by this f, you will know if that was the limit point or not, because there is just one y, and so in particular one neighborhood that you will miss in a certain sense. And so you will know whether you're given, like whether your initial data was essentially the empty enumeration or not. So in particular, this allows you to conclude much more than just sort of what points you need to avoid. I mean, you also get to know if you had to avoid a point to begin with. So I guess this is maybe a bit of a stretch to define this as an example, but via this method we recover the result by Weihrauch, for instance. Okay, and in the other case, actually, there is no reason to read this slide because we already produced sequential ACCN, which is what we wanted. So yeah, so if f computes ACCN, then in particular computes the other guy, which satisfy the hypothesis that we wanted to satisfy. Okay, but we can actually say more if we look at sort of equivalent formulations of discontinuity. So, for instance, if you look at discontinuity via Wadge games, okay. So, just to remind what Wadge games are. So, consider f from bare space to bare space. The Wadge game for f is the following game. So, it's played between two players, player 1 and player 2. And at every turn t, player 1 plays a string, potentially an empty string, in I mean of natural numbers, and player 2 responds by playing another string again, which can potentially be empty. And essentially, the final play of player 1 is just obtained by concatenating all the small strings that player 1 played so far, and similar for player 2. So we call it this x1 and x2. So, but notice that since we were sort of quite generous when it came to what they were allowed to play, they might actually output, I mean, not reals, they might output funny strings. But anyway, so we say that player 1 wins if either player 1 is in one of the cases that I said above. So if it fails to produce something which is in the domain of f, or otherwise player 2 also wins if essentially if he is able to guess the image of the point that was produced by player 1 according to F. And if otherwise, player 1 wins. Okay, and something that Uno, Braga, and Arno proved is that a function F from a partial multifunction from bare space to bare space is continuous if and only if player 2 has a winning strategy in the Wadge game for F. And essentially, here we go back to what I was telling you before in a certain sense. So what does the strategy 2 do? So the strategy for player 2 gives the approximation that you wanted. So it gives you the approximation of the realizer of the function F. And on the contrary, if we had a strategy for player 1, so supposing that the player 2 does not win, but player 1 does, so the player 1 has a winning strategy, then you can sort of see the strategy as the witness that F is continuously discontinuous, which is what I was telling you before. This is what AD does for in the general case. So what does a strategy for player 1 is essentially something that tells you that no matter how hard player 2 tries, not only you're sure that you will be producing something in the domain, you're also sure that you will be able to defeat sort of player 2 best attempt to make you, I mean, to guess the image of the points that you're producing. And this in a certain sense closes the should explain what I was rambling about on the previous slides. Okay, so and now let's restrict again, instead of restricting the sort of the domain of the discontinuous function, let's restrict the codomain. So now let's consider a function from a partial multifunction from a represented space X to N, so the natural numbers represented the way I was telling you before, and assume so let's assume that F is discontinuous and also assume that the Wadge game for F is determined. Then what I claim is that again, under these assumptions again, this function sort of continuously Weihrauch reduce. Well, ACCN continuously Weihrauch reduces to this function here. And well, sketch of the proof is essentially it basically go back to what I was telling you in the end of the previous slide. So we can conclude by determinacy that player 1 has a winning strategy. We can call it S. And then what is that we need to do? Essentially, well, not much in the sense that in order to prove the reduction, we can just essentially pretend that player 2 is playing the empty set as long as the enumeration does nothing. I mean, as long as the enumeration enumerates nothing. And as soon as the enumeration enumerates n, then we pretend that I mean, so we act as if player 2 was playing the natural number n. And then we're essentially done. I mean, by the fact that sort of by the assumption that we know that any k in f of x1 will not be n, we actually proved a strong reduction in I mean a strong reduction between ACCN and the function f. But the point, I mean, the interesting thing is that if you closely examine the game that was being played before, the game is actually I mean, you don't need any form of determinism. So for every f, the Wadge game for f is determined in the sense that you either can come up with a strategy for player 2, or you can come up with a strategy for player 1. And yes. It's multifunctions in both. So what do they do? No. It's no. It should be sorry. Yes. So yes. So yeah, the idea is what is essentially that. So either the function is continuous, or if it is discontinuous, then the game is too stupid for player 1 to lose, in the sense that player 2 only has one legal move, and it's easy to diagonalize against it as long if you know that your function is discontinuous. So we actually, no amount of determinacy is needed in this case. So we can summarize what is going on, right, by essentially by putting together the results that we gathered so far. So the following are equivalent for a partial multifunction between x and y. So ACCN continuously reduces to this f, or you compute a discontinuous G with codomain n, or your domain has this. I mean, so you can restrict your domain to have this particular shape that we were discussing before. And okay, okay, if you actually go through the proof, you notice that, I mean, we actually need both functionals in the reduction to be continuous. You cannot get away with any of them to be just computable. But okay, this is a minor remark. Okay, so, but what happens for larger dimension? Okay, so now let's, and this will need some amount of terminology, unfortunately. So let F and G be problems between represented spaces. We define the sum of F and G to be defined as follows. So the input of F plus G is any pair X, which is in the Cartesian product of the two domains. And the output is something, unfortunately, I mean, something which is quite complicated. So the output is, well, this set here, where the Y's, so Y bar and Z bar are the completions of the corresponding spaces. Okay, so this is the formal definition of completion. This is unfortunately quite complicated. But so the main idea of what is going on is the following. So the completion of a space is essentially something that allows you, so if you start with a space X, you obtain the completion of it by sort of augmenting the space with a point which represents, in a certain sense, the garbage. And you make your representation, I mean, even if it wasn't total when you started, it will be total now. And what you want to do is essentially, now you want, like we're looking at the representation of a point, you essentially want the symbol 0 to mean that you don't really want to give any information about the point you're representing. What do I mean by that? I mean, what I mean is that, so if you, so given a representation of any point, is after you get rid of all the zeros, you're left with something that was a name of the point in the previous sort of in the standard representation of X. Then this is actually the point you're representing. Otherwise, if you have to, like, for instance, if P is just a constant zeros, then you're just saying, okay, I mean, this is not a point, this is garbage, and you're representing this point that you added. So going back to the problem we were defined, so the sum of F and G. So what is going on here, essentially the idea to have in mind is that given X and given inputs X and W, we want to solve F or G according to, so we want to find a point in F of X or a point in G on W, but we absolutely don't care about the other component. In particular, so the other component could be, I mean, it could be, the output could be absolutely nothing. I mean, not only could it be wrong, it could actually mean nothing in a certain sense. Okay. And of course, well, maybe not of course, but we can, there's no reason why you should stop this operation to be, why you should just be willing to add two problems. You might want to add n of them, and we actually do. So the nth sum is the finite generalization of the sum, and you can check that sort of this operation is associative in the strong Weihrauch degrees. And you can actually define the infinite sum, essentially with the same idea. I mean, I'm not going through the definition, but the idea of the infinite sum is what? So you're given, you take infinitely many, so countably many instances of F, and you want to be able to solve at least one of them. So yeah, it actually is the obvious generalization to the infinite case of the sum. Okay, and let's say if we had to put an order on them, what's happening is this. So your F will be stronger than any amount of finite sums of F, and every time you add one F more, you get something which is definitely not stronger. And in particular, well, this also carries on to infinity. Okay, so results for larger dimensions. So what I want to prove is the following thing. So the following are equivalent, essentially. So this time it's equivalent for your discontinuous function to compute the nth, the sum of n many ACCN, and to have sort of a nice sequence in the domain in this sense. So what you want is essentially sort of having what you have expected to have the Cantor-Bendixson rank n+1 in a certain sense. So what is this space? So you can actually see this space as being, I mean, something like this. So you have an infinite, you have a sequence converging to a limit point, and you actually have infinite many sequences converging to a certain point, and then you also want these limit points to converge to some larger limit point. So for instance, this guy is what Z2 looks like. So essentially, you have limits and you have limits of limits. This is just a sort of a convenient way of representing the space. And if you want to go on with dimension, you will also have a limit of limits and so on. I mean, it's nothing particularly complicated to have in mind. And this is in a certain sense what I mean, the obvious guess of how you should generalize the result that we had above. So, and in this case, what happens is that like the reductions that were not necessarily strict before become strict now. So ACCN will be, so this actually is a proper descending sequence of principles. And something which is also maybe interesting to notice is that, that was actually, again, noticed by Brattka in another paper, is that in the infinite case, we recover the discontinuity problem that was, I mean, that Brattka defined. So, yeah, which is, I guess, a nice picture. Right, and something which is also maybe interesting to say is how to prove this theorem in a certain sense, because so ACCN is sort of the right degree, but not exactly the right space to work with when you want to prove this result. Okay, so and something that is maybe quite interesting is that the best version of like the best representative of this degree to work with is actually a problem between weird topological spaces in a certain sense. So, well, this is quite not the easiest thing to read. So let's use an example, I guess. I mean, it's a bit too small, but the idea is that we want to use sort of instead of using n. Okay, so we want to define two spaces essentially. So this will be the starting space of the function that we want to define, and this will be the arrival space of the function we want to define. How are they? What are these two spaces? So the space is essentially given by these guys. So points are sequences of zeros and non-zeros guys, such that essentially you only care about the last non-zero number appearing in the sequence and the number of non-zero numbers in the sequence that you're examining. So, and this is what I mean here. So, and you also know that there will be at most n many numbers that are not zero in your sequence. Yes. Could I draw that? I could definitely try, but so what I did, since I knew this would be, I mean, even LaTeX is not particularly good at picturing that. So it's good to have the dimension 2 in mind. And so what happens for dimension 2? Essentially, the case for dimension 2 is the following. So n over n is simply the following point. So you're given as inputs a sequence of zeros. So if you scan the name of your point, you will have some zeros. Then at a certain point, you might find something that I called n. Not the best choice of name. Okay, so if it so happens that you never find anything else, so if all of the remaining sort of digits are 0, then this is a name for the point sort of n, and you don't care about the second component, so we just use a dot. If instead at a certain point, not only do you find an n, but you also find an m, and then I mean necessarily all the rest will be zeros, then you start caring about the first component, and what you care about is the second component. So, and you say that this is a name for the point dot, which means, I mean, which represents the fact that we don't care, and then m, which is, I mean, yeah, which is actually the second meaningful digit that we found in our representation. And when I add a bottom here, what I mean is that I also allow, well, essentially the limit point. So in this case, we know that there will be at least one non-zero m showing up in the representation, whereas in this space, we were given no such guarantee. And again, the idea is that, yeah, here we have something to converge to. And now this is the, I mean, for sort of weird reasons, the problem that you actually want to work with when it comes to proving the theorem that I stated before. So yeah, the real problem you want to use is this. So you want inequality between so the problem, which is the inequality from the larger space to the smaller space. So this is the problem such that for every x in sort of the sequence of n natural numbers and the bottom, it gives you everything which is not that point. So notice that in particular, if x is bottom, if you're given so the sequence of all zeros, then you can output whatever you want and you will be happy. In all the other cases, you will be excluding 1 point. Now again, it's easier to see that this guy is discontinuous essentially for the same reason that sequential ACCN was discontinuous. I mean, as soon as you fix a potential image of the limit point, it's very easy to find something that avoids it. And okay, so what is going on here? Again, there is no need to use any oracles. We can actually show that inequality for this space with bottom is actually Weihrauch equivalent to n sums of ACCN. And what is going on here? Well, I'll maybe skip this, except for the second one. So in a certain sense, the second one tells you what it is that we don't like about ACCN. So and so we will maybe see in the next slide, ACCN has a major drawback, which is it distinguishes between n components, whereas we don't really want that. I mean, when working with sequences, what we actually, we just care essentially about, in a certain sense, we just care about your counterbanding some degree. ACCN contains too much information, which is not necessary, which makes the proof of a reduction cumbersome. And the point of this guy, the point of this inequality is that this guy is perfectly happy with ignoring, the only thing that is telling you is basically, the only thing is care about is your counterbanding some run. And in a certain sense, this is what is going on in this reduction here. So in order to make this reduction work, you actually have to come up with a, in a certain sense, with the coding that allows you to tell, okay, it's true that ACCN actually cares about which component you're solving, but that's not really important. And this is essentially what happens in this case. Okay, this is maybe not the best explanation, but this is the idea of what is going on. Why we want to go via an intermediate step, and this is something in a certain, and this should also explain why nothing like this was essentially necessary in the case of dimension 1. There are no components to mess around with in that case. That's one. Okay, so and a sketch of the proof of the theorem that I actually mentioned is the following. So okay, again, the direction 1 to 2. In this case, I didn't necessarily give you something which is a problem with domain Zn, as I did in the case of dimension 1, where sequential ACCN did the job perfectly. But it's not difficult to sort of come up with one. It's and to generalize the inequality problem that we had before to actually have the domain we want in this case. It is perhaps more interesting to see what's going on in the like for the other direction. To show that if you compute anything like this, then you're actually able to compute the sum of n ACCNs. Okay, and what is going on here? It's in a certain sense what we have to come up with is, so to speak, again, an alternative character. So we have to be more precise about where a function is discontinuous in a certain sense. So for every point, we want, in a certain sense, to have an open set of bad points in the image of this point. So and we defined it inductively as follows. So as long as you're not a limit point, this open set is 0. But if you're a limit point, then we actually care, in a sense, what we care about is the following open set. So we want to consider the strings such that definite strings describing a open set such that there exists a sequence of points converging to this open set with the following property. So the intersection of the images of the sequence of points between your point, it might be not empty, but it has to be empty after you remove the bad open sets that you defined for the points in the sequence. And you can assume that you have defined them essentially by induction. And the induction has to be seen essentially on the rank of the points. And UM is just the open set generated by the by these strings that you define. And the point is what? The point is that F is discontinuous if and only if you're able to find a point in Zn such that the entirety of its image is contained in this open set of bad points, which is essentially the reason why I call them the open set of bad points. So essentially, what is happening here is I'm saying, so UN is describing the set of points in the image such that, so you read the discontinuous for trivial reasons, in the sense that you can find something, yeah, so you can find a sequence of points that converge to you, but the image of that point, or of those points is disjoint from the image of this limit point that we're considering. Or maybe you actually, you get to hit it, the image of this limit point M, but the price you have to pay is that you will be necessarily landing in points that are bad for something in the sequence converging to you. Yeah, sorry, it's a bit convoluted, but so the idea is essentially to go down the rank of points in your domain and saying that essentially either you're bad, or even if you're not bad, you're forcing some points before you to be bad. And how is the reduction proved? Well, no, well, thank you. But so how is the reduction proved? Essentially, what we prove is that without loss of generality, you can assume that the bad point is the the ultimate limit one, and then using as oracle all of these function, all of this sequence of badly behaved points that converge to you, you are able to replicate, essentially to replicate the proof that we had for dimension 1. And right, so something that I should, and so it's essentially, this is what you need to make an inductive argument out of the case for dimension 1 in a certain sense. And well, using the semi-officially terminology of this conference, I guess that this is a theorem star that you can actually, I mean, also the third condition can be proved. I mean, even if we had, so if instead of having conditions on the domain, we have a condition about the rank of the codomain, then we again have an equivalence. Again, we have an equivalence in the sense that if you're discontinuous and your codomain is something of the Cantor-Bendixson rank of this guy -1, essentially, then you're able to compute the n sum of ACCN. And now, yeah, thank you very much for your attention. These are some references.
Any questions? Vasco.
Yes, so I have, first of all, thank you for your nice talk. I have a question to the first part of your talk where you had this result about ACCN being a lower bound for problems with codomain natural numbers.
Yes.
I think it was formulated as, yeah, okay, this theorem, exactly the equivalence of the first two items. So there is this notion of a first order problem that was first order variant of a problem that was introduced by Zafarov and others, and you studied that intensively with Manlio Valenti.
I did, yeah.
My question is whether this result doesn't give rise to a dual version of this notion where you have kind of a lower first order variant. So where the question is this the minimal degree with codomain natural numbers, which is above something? So could I read the equivalence of these first two things here as the statement that the lower version, the lower first order variant of the discontinuity problem is ACCN?
Good question, interesting question.
I think there are a lot of dual things happening here. So you mentioned that the discontinuity problem is the infinite sum of ACCN. So that's what I call stashing, and that's kind of dual to parallelization. And similarly, as you have proved and seen that the first order part of a problem, when you parallelize it, often gives you back the original problem. Here we have kind of a dual situation. And so I think it would be worth studying the lower first order part of a problem, which would be the minimal thing with codomain natural numbers that is above something.
very interesting point. Yeah, thank you very much. I didn't think of it this way. Yeah, but yeah.
Okay, thanks.
Yeah, thank you.
Can I ask a question back to Vasco? So my question back to you, Vasco, would be whether it's obvious that that if something is below something with codomain n, that it is below something minimal with codomain n. Or would that be one of the first things to check when studying this potential dual?
Of course, you would have to check such things. I haven't studied this lower first order dual thing here, but it just reminds me of it, and it's a very similar situation, right?
Yes, I agree.
Other questions? I have a question. You have, thank you for a nice talk. You have mentioned in some cases that the Weihrauch reduction is in fact a strong Weihrauch reduction. And I saw in a few others that, for example, with these join ones, that the reduction could be strong. Are there any of these reductions that you know that it's necessary to use a Weihrauch instead of strong Weihrauch to obtain the result?
Yes. Oh, well. So I know plenty where in the I would have not the slightest idea of how to, I mean, yeah, make the proof be a proof of a strong reduction, but I don't actually, I mean, of essentially nothing. I think we proved that this is, I mean, we just have Weihrauch reductions instead of having no, I mean, and they cannot possibly be strong Weihrauch reductions. So yeah, like for instance here, for these problems here, I mean, the proof is a Weihrauch reduction, but I mean, just because I would have no idea, I mean, we would have no ideas how to make them, how to make the strong Weihrauch reduction, and I would be very surprised if they were strong Weihrauch reductions. But in principle, I don't see any reason why they shouldn't be strong Weihrauch reductions in a certain sense. This is what I was trying to say. So, yeah, I don't know would that be the shortest answer, right? Probably. Yeah. Yeah. Thank you.
Any other question? All right, let's thank Giovanni again. Resume at after the tea. We'll resume at 4 p.m.